In a hydraulic system, actuators convert hydraulic energy. But to do useful work like moving loads and to prevent damage to the system, the hydraulic energy has to be controlled. Typically, 4 kinds of hydraulic valves are used to control the transmission of energy: pressure control valves, directional control valves, flow control valves, and check valves. Let's begin with pressure control valves. In a hydraulic system, pressure will increase to overcome the resistance of the system. For example, when a cylinder piston reaches the end of its stroke, pressure continues to increase. Without a pressure control valve in place, the pressure in the system could eventually rupture seals, stall the drive motor, or even burst piping. In short, pressures could reach unsafe levels. Pressure control valves generally consist of a valve body with an inlet port, an outlet port, an internal moving part called the spool, and a spring at one end of the valve which biases the spool. That is, the spring holds the spool in position at one end of the valve body. At the other end, a small internal passageway leads from the inlet port to the end of the spool opposite the spring. If the spool is biased so it blocks the flow of fluid between the 2 ports, we call it a normally non-passing pressure control valve. When pressure is applied through the inlet port, the force against the inside ends of the spool is the same in both directions, so it cannot shift, and the outlet port remains closed. At the same time, however, pressure is applied through the internal passageway against this end of the spool. At first, the tension of the spring keeps the spool in place. Once the pressure in the system is high enough to overcome the tension of the spring, the spool moves, compressing the spring and opening the outlet port. Fluid flows through the valve, maintaining the pressure in the system. The spool remains in its shifted position, and the secondary port remains open until pressure in the system drops below the tension strength of the spring. When that happens, the spool moves back to its normal position, closing the outlet port again. The fluid pressure which actually moves the spool is known as pilot pressure. Pilot pressure is a common way of operating many types of hydraulic valves. A pressure control valve is often installed with its inlet port connected to the pressure side of a pump and its outlet port connected to the tank. This allows flow from the pump to return to tank so the system pressure doesn't become excessive. A normally non-passing pressure valve used like this is called a pressure relief valve. The second kind of control valve we need to talk about is the directional control valve. These valves control the direction in which actuators move by controlling the direction in which fluid moves through a system. For example, a directional control valve on a forklift allows us to use hydraulic pressure and flow to raise the load or to lower it, depending on which way a valve control lever is moved. Let's see how this is done. Most cylinders in use today are double acting. That means they can apply force in both directions. They have a port at each end, and the piston will move in either direction. Which way they move depends on which port is being used as the inlet port and which port is being used as the outlet port. We've labeled these ports A and B. When hydraulic fluid flows into one end of the cylinder through port A, it forces the piston to move in one direction. As the piston moves, it forces the fluid at the other end out port B. When fluid flows in through port B, the piston is forced back in the opposite direction. As it moves, it pushes the fluid ahead of it out port A. To control which direction the piston moves, we use a directional control valve. It works by determining which port on the double-acting cylinder is used as an inlet port and which is used as an outlet port. A typical directional control valve consists of a valve body with 4 ports and a sliding spool. The spool connects and disconnects passages within the valve body. For ease of identification, we'll label the 2 top ports A and B. Port A on the valve is connected to port A on the cylinder, and port B on the valve is connected to port B on the cylinder. We'll label the other two ports on the valve P for pump because it's connected to the pump, and T for tank because it's connected to the tank. When the spool is centered, all four ports are blocked and no flow is possible. However, if the spool is moved in this direction, the passage from the pump to port B on the valve and port B on the cylinder is connected. At the same time, the passage to the tank from port A on the cylinder and port A on the valve is also connected. Fluid flows from the pump through the valve and into port B on the cylinder, pushing the piston in one direction. As the piston moves, fluid is forced out port A of the cylinder through the valve and back to tank. To move the piston back in the other direction, the valve spool is shifted in the other direction. When this happens, the passage from the pump to port A on the valve and port A on the cylinder is connected. At the same time, the passage to the tank from port B on the cylinder to port B on the valve is connected. Fluid flows from the pump through the valve and into port A on the cylinder, pushing the piston in one direction. As the piston moves, fluid is forced out port B through the valve and back to tank. As the spool shifts back and forth, the cylinder also moves back and forth. If the cylinder piston reaches the end of its stroke, or if the spool keeps all four passages blocked, a relief valve prevents pressure in the system from becoming too great. As soon as pressure reaches the relief valve setting, fluid dumps to tank until pressure drops below the relief valve setting. A similar system is used on a forklift. When the operator shifts the lever, it moves the spool of a directional control valve in the lift's hydraulic system, raising or lowering the forks. When the operator leaves the shift lever in one position, even in the closed position, a relief valve prevents the continuing pressure from damaging the system by directing fluid back to tank. Now, sometimes it is necessary to control the velocity or the RPM at which an actuator moves. To do this, we use a flow control valve. We learned in an earlier lesson that the velocity at which actuators operate is determined mainly by the rate of flow. Flow to an actuator can be controlled by selecting a pump with the required flow rate. For example, if an actuator needs to move at a certain velocity that requires a flow of 5 gallons per minute, we could select a pump with a 5 GPM flow rate. However, in many hydraulic applications, the size of the pump is based on the maximum flow requirement of the system. That is, the system's peak demand. As a result, large actuators may operate too slowly, while small actuators may operate too fast. Flow control valves are used to adjust actuator velocity by adjusting the flow rate to different parts of the system. These valves consist of a valve body and an internal part which moves in and out of an orifice. In one of its simplest forms, a flow control valve has a threaded rod with a tapered nose or needle which can be adjusted in or out to change the flow. Adjusting the needle varies the flow restriction, increasing or decreasing the flow rate through the orifice in the valve. If flow from the pump is continuous, restricting the flow reduces the velocity of the actuator but increases pressure. To keep pressure from rising too high as flow is restricted, systems must include a pressure relief valve. If adjusting the flow control valve causes the pressure to rise to the relief valve setting, the pressure relief valve will open, allowing a certain amount of the fluid to return to tank. The last kind of valve we need to look at is one of the simplest, the check valve. Check valves prevent fluid from flowing in more than one direction. A check valve has a body, an inlet and an outlet, and a poppet or ball which is biased against one end of the valve body by a spring. The valve also includes a seat for the poppet or ball which effectively seals off the line when the poppet or ball is in place. When fluid pressure at the inlet port is high enough to overcome the tension of the spring, the poppet or ball is forced off its seat and fluid is allowed to flow freely in one direction. However, if the flow is reversed, the poppet or ball is forced back into its seat and prevents fluid from passing. Check valves are often used as bypass valves, allowing fluid to bypass or flow around another component in the system. This is sometimes done, for instance, to speed up the cycling of actuators. In this system, for example, the check valve prevents flow in this direction, so all flow must pass through the flow control valve. Therefore, the cylinder rod runs out at a velocity determined by the flow control valve. However, on the return stroke, the check valve opens, permitting much greater flow and allowing the cylinder to complete a cycle much more rapidly. Check valves are also often used to isolate sections of a system. For example, the check valve in this system prevents flow from other parts of the system from dumping back through the relief valve or running the pump backwards. Finally, check valves are also used to hold loads in place. This is possible because there is very little leakage past the poppet or ball. For example, the poppet in this check valve forms a seal tight enough to suspend a cylinder's load as long as other components or parts of the system do not leak or fail. Other valves we have seen generally permit more leakage than check valves because there are no seals between the various ports. The close fit between the mating surfaces are all that prevent the passage of fluid. And in many cases, some leakage is actually required for proper lubrication of the valve as it operates. When the time comes to move a load held in place by a check valve, we need a way to force the poppet in the valve off its seat. This requires a special valve called a pilot-operated check valve. It is similar to a regular check valve, except for a small piston that's operated by pilot pressure. In this check valve, pilot pressure moves a spring-biased piston, which forces the poppet off its seat. As long as pilot pressure remains high enough to compress the spring, fluid can flow in either direction. When pilot pressure drops, the spring moves back, the poppet reseats, and the valve once again works like a regular check valve. In some instances, it's necessary to stop a load in place so it won't move either way. To do this, we can install two pilot-operated check valves. Each line into the cylinder provides pilot pressure that keeps a check valve on the opposite line open, so fluid can flow in both directions. However, when pilot pressure is removed, both valves reseat, and the load may be locked in place. For example, a pilot line from line A in this circuit opens the check valve in line B, so fluid can flow out of the cylinder through line B. Similarly, a pilot line from line B opens the check valve in line A, so fluid can flow out of the cylinder through line A. When system pressure is removed, however, the poppets in both check valves reseat and the cylinder stops. It's never a good idea, however, to rely on any one component, such as a check valve, to keep a load locked in place. Hydraulic systems can and sometimes do fail. If safety is at risk, always use a mechanical load lock to keep the load in place. Now, all of the hydraulic components we've seen in this lesson have been illustrated as though they were simplified cutaways of the real thing. Schematic symbols are a standardized method of representing both the components and the layouts of hydraulic systems. For example, this drawing represents the simple system we've developed so far. This kind of representation is called a schematic drawing. The lines represent the system's piping, some of which cross without joining. For lines that do join, a dot can be used to indicate the connection. Pilot lines used to shift spools and other movable members are represented by a dashed line. This is the symbol for a pressure control valve. It includes a representation for the normally non-passing spool and the spring which biases the spool in place against the end of the valve. Notice the pilot line and the symbol for this valve. A directional control valve, which looks like this in one position with flow going from P to B and A to T, is diagrammed like this, and in the opposite position like this. Or the two are combined to show a two-position valve like this. This is the schematic symbol for a double-acting cylinder, which might be used with a directional control valve. These are the two ports, A and B. The symbol for a check valve, even though it may operate with a poppet, is always shown with a ball. It's easy to remember the direction of flow through a check valve if you keep in mind that the angle here represents the valve seat. Flow in this direction is stopped as the ball or poppet is forced onto its seat. Flow in this direction unseats the valve. Flow control valves are represented by a symbol like this. The arrow indicates that the flow rate is adjustable. Hydraulic pumps are usually driven with electric motors. This is the symbol for an electric motor. The arrow indicates a shaft which rotates in one direction only. This is the symbol for a pump. The single solid arrow indicates the direction in which fluid moves through the pump. A reservoir or tank is depicted schematically like this. Lines returning to tank are shown like this if they return below the fluid level, and like this if they empty above fluid level. Filters are also frequently shown. This is a filter symbol. In this lesson, we have shown 4 basic types of valves used to control hydraulic energy. We've also seen how hydraulic systems can be represented schematically with symbols for the system's components. In the next lesson, we'll look at accumulators, which store hydraulic energy, and at cylinders, which use the energy to perform work.